Take two. So I guess I'm pretty long-winded. So I got a timer on my phone set for 45 minutes. So I won't go over that. I think the lengthy videos pose a problem. So alright, so we're talking about current that's passing through a wire. First thing we got to mention is, why is there current passing through a wire? The only way I can move charge is due to an electric field. And so towards the end of this chapter, we'll see that we have to apply a potential difference and generate an electric field inside of a wire to move electrons. So electrons are what move, right? A conductor is a lattice structure, right, where our atoms are bound to one another. They don't move, but our valence electrons, our free charges, are what's actually moving. So how many electrons are moving? We're going to call that capital N sub E. So how many electrons are passing through a cross-sectional area of a wire? Right, so I drew this picture here of a wire. I drew it as cylindrical, and this little slice here is a cross-sectional area. So we're going to say the electrons are moving in the positive x direction. That means in this case it's due to an electric field in the negative x direction. So the electrons are moving some displacement delta x, and they're passing through a cross-sectional area of the wire. So we're going to call lowercase I sub e the electron current, okay, and that's the number of electrons passing through a cross-sectional area of wire over some time interval, okay. And I can rewrite it in terms of the current. Divide both sides by delta t. So these are units of inverse seconds, right? Electrons per second. This isn't like a real SI unit, so it's just a number, okay. So a useful thing to know is how many electrons are inside a certain volume of wire. And I use lowercase ol in my subscript to denote volume, because we've got capital V's all over the place for voltage and potential difference. So V sub ol is going to be volume. We're going to call this the charge density. Okay, so the number of electrons per unit volume in a wire. So you have a section of wire with a volume, and we want to know how many electrons are in that volume. Okay, so lowercase n sub e is going to be called the charge density. So we've got charge density, we've got number of electrons, this is my volume V. Alright, so for any shape of wire, we're going to assume they're cylindrical most of the time. The volume is the cross-sectional area times a given length, right? So if we picture a cylinder, the surface area is pi r squared, and then multiplied by the height, we get the volume of a cylinder. That's my formula. But this is just a general expression for the volume of a wire. So any cross-sectional area times any distance, any length of wire, any section of wire, delta x. So I'm going to take this A times delta x and substitute it in here for my volume. But electrons have a drift speed. What does that mean? They have a drift speed. So they're moving very quickly inside the wire, but there are multiple collisions. They're colliding with each other. They're colliding with, quote unquote, colliding with the nuclei. But together as a group, if there's an electric field, together as a group, they're all moving very slowly in one direction. So even though they have very, very high drift speeds, or very, very high speeds, like we saw in chapter 16, when they were in the presence of an electric field, they're constantly colliding with each other. But they have a very, very slow drift speed. But the reason your light bulb turns on instantaneously is because a wire over here will hit, or an electron over here will hit an electron, and then there will be kind of like a chain reaction. And so any motion in the electrons over here will instantaneously, almost instantaneously, cause a reaction or motion of electrons over here. but the drift speed is the speed of all the electrons together as they're moving. So that's going to be very slow. So from 120 we've got our drift speed, right? Classical mechanics, for a constant velocity it's delta x over delta t. So I can rewrite delta x, right, a certain length of wire. I can rewrite that as the drift velocity times time. And so now I have this new expression for number of electrons, capital N sub e. But if I take this expression for capital N sub e, and this is just my derivation of what's on the slide. If I take that expression for capital N sub e and I substitute it in for my current, my electron current expression, the delta t's cancel out and I'm left with this. So I'm left with another expression for the electron current right here. Okay. So if I knew the drift velocity, I knew the cross-sectional area of the wire, and I knew the charge density, I could calculate the current, right? Or if I knew the current, I could calculate the drift speed. So charge density, we don't really have an expression for that yet, but there is a way to find the charge density of a certain material. And so I'm going to go through this, how I derive charge density given some properties of a material. So what I want is I want charge density. So I want electrons per cubic meter, right? So basically I'm just doing some work with units and some properties of the material to get some value that has units of electrons per cubic meter. So we're going to start off with two quantities that we can either look up on the internet. If we're on an exam, I'll certainly give you that information. But if we're doing a problem like a WebAssign and they don't give us these values, we can go on PubChem or the internet or something like that and find these values. So those two values are the molar mass. Usually it's given in grams per mole. I'm going to want that in kilograms per mole. Or at the very least, I'm going to want these mass units to be the same. Then we have the density, right? Lowercase rho for density. So I looked up these two values for copper, all right, the molar mass of copper and the density of copper. Now the first thing I want to do is I want to calculate the molar density, which is the ratio of the material's density and its molar mass. So this is the molar density. What's going to happen is I'm going to have kilograms per meters cubed in the numerator. If you look it up and it's in grams per centimeters cubed, okay, at least make sure that this is converted to cubic meters, and make sure these masses are the same because you want them to cancel. So I'm going to have kilograms per meters cubed in the numerator, and I'm going to have kilograms per mole in the denominator. So what happens is my kilograms, or if you leave them both as grams, they will cancel out, and I'll be left with 1 over meters cubed over 1 over moles. I have to multiply the numerator by the reciprocal of that, and I'll get moles per cubic meter. So the first thing I want to do is find the molar density, and that's the density over the molar mass. All right. So for copper, when I plug these values in, I get 1.4 times 10 to the 5 moles per cubic meter. So that's my first step. Given the density and the molar mass, calculate the molar density. So now I have the molar density. I want to convert moles to number of atoms. So I'm going to multiply my molar density, rho over m, by Avogadro's number. So that's number of atoms per mole. Alright, so I'm getting rid of the moles and I want atoms. So now this value right here, we can call it atomic density, right? Number of atoms per cubic meter. So what I do here for copper, I have this value, I multiply it by Avogadro's number, and I get this number, but I'm not quite done yet. because every atom in a conductor will either give up one free electron or two free electrons. So that's information that I would give you, or that we could look up. For copper, it's one free electron per atom. So once I get this number here, my molar density times Avogadro's number, that's my atomic density. I want to multiply it by either 1 or 2, depending on how many free electrons the material gives up. Why do I do that? Because I'm getting rid of atoms, and I want this to be in electrons per cubic meter. Right, that's my final expression. Right, I want charge density, number of electrons per cubic meter. So density over molar mass times Avogadro's number times the number of free electrons per atom, I get the charge density. Okay, so that's basically our process here. All right. So what is really happening here is I'm talking about current in terms of electrons, right? But as we can tell, charge density is very large, so there are many, many electrons that are passing through that cross-sectional area. What I want to do is I want to talk about moving charge in terms of coulombs, right? Because coulombs is a more practical unit of measurement for moving charge. So the charge of an electron or a proton is plus or minus 1.6 times 10 to the negative 19 coulombs. So I want coulombs in terms of the fundamental unit of charge. So if I divide both sides by this number, I get 1 coulomb is 6.25 times 10 to the 18 units of charge, right, or E. So this is more practical, right? I actually want to deal with current in terms of coulombs. So this is my conventional current. All right, my conventional current is the number of coulombs passing through a cross-sectional area with respect to time. Okay, so lowercase I sub e is little current, electron current, and capital I is my conventional current. That's my big current that we want to deal with. So the SI unit for current is the ampere. We say amp for short. So those are coulombs per second, right? Number of coulombs passing through a section of wire per second. All right. So how do I get capital E from the electron current? I just multiply it by the fundamental unit of charge. So if I have the electron current, I sub E, multiply it by 1.6 times 10 to the negative 19 coulombs, I get coulombs per second, and I have my conventional current. So another way I could write my current is substitute N sub E times the cross-sectional area times the drift velocity in for the electron current. And this is another expression that I could use if I'm asked for the conventional current. So we've got a lot of variables, a lot of expressions, a lot of stuff to keep straight, but I try to focus on the main ones, you know, by highlighting them in the slide here. Okay, so let's do an example. We've got an iron wire, and it's got a cross-sectional area of 5 times 10 to the negative 6 square meters. Sometimes they'll give you dimensions in centimeters or millimeters, so just make sure you can convert your, you know, square centimeters to square meters or whatever. So given the density and the molar mass of iron, right, we go on PubChem or, you know, some website or something like that, we find these values, or they're given to us, right, if we're on an exam. Compute the molar density of iron in moles per cubic meter, then calculate the atom density of iron, and then part C, find the charge density, right? This is electron density. Sometimes you'll see it as number density or free charge density. I usually say charge density, something like that. So for iron, we have two conduction electrons per iron atom. So when I go through this whole process and I find the atom density, I'm going to multiply it by 2 electrons per atom to get the charge density. Final part, if the wire carries a current of 30 amps, so let's say we measured with an ammeter and we get a 30 amp current through the wire, we're looking for the drift speed of the conduction electrons. So the first thing I'm going to do is I'm going to look up my density for iron. So notice for density I use a subscript of the element, or the alloy, whatever it is. And the reason I do that is we're going to use rho for something else later on. So if you see rho with a subscript of an element's chemical symbol or whatever, I'm talking about the density. Plus, the units should be a good identifier too. So I looked up the density, looked up the molar mass, and I kind of cheated a little bit. I used Google, and I made sure to find it in kilograms per cubic meter and kilograms per mole, so I didn't have to convert any units. So I'm finding the molar density, rho over m. So when I substitute these values in, I get 1.4 times 10 to the 5 moles per cubic meter. All right. Watch our powers of 10 here. All right. Sometimes I see people like subtract 2 from 3 or something like that. So this is 10 to the third power divided by 10 to the negative 2. So it's going to be 10 to the 5. Okay. 1.4 times 10 to the 5 moles per cubic meter. That's part A, molar density. Part B is the atom density. We want the molar density times Avogadro's number. So it's atoms per cubic meter. We should be getting a very, very large number here. All right, so once we get to this step, we should be getting a very, very large number, very large power of 10. Okay. So multiply by Avogadro's number. My atom density is 8.5 times 10 to the 28 atoms per cubic meter. Part C, I'm looking for the free charge density, or the electron density. The problem says that an iron atom gives up 2 valence electrons, and so I multiply my atom density from part B by 2, and I get the number of free charges per cubic meter, 1.7 times 10 to the 29. Part D says we measured the current. We've got a conventional current, big I, of 30 amps. So I need to find the drift speed. So I went back and I found this expression right here. So E N sub E A V sub D. So I have the current. I know what the charge of an electron is. I just got the charge density from part C, and I was given the cross-sectional area. So I have everything I need. Just got to do a little bit of algebra, isolate the drift velocity term, and then I can calculate. So I'm dividing both sides by the charge density, fundamental unit of charge, and the cross-sectional area. So I've got a nice expression for the drift velocity. Plug my values in, and I'm going to get a very, very low drift velocity. All right. So it's kind of counter to what we were getting when there was a free charge and electric field from chapter 16, which was very high. But again, we've got those multiple collisions, and the sea of electrons is moving very slowly. Okay. So let me check my units just to make sure, right? An amp is a coulomb per second. So coulomb per second's in the numerator. This is a unit I can ignore. That's just the number of electrons. I've got meters cubed in this denominator. I've got coulombs and meters squared. So 2 of my meters are going away. My coulombs are going away. I've got 1 unit of meters left in the denominator of my denominator, so that comes all the way up to the numerator. These seconds are in the denominator, so I'm left with units of meters per second. So I'm good. I did all my algebra right, got my units correct, so I'm feeling good about my answer there. A useful quantity is to investigate is current density, right? So that's current per square meter, so current per area. So we were talking about a little bit earlier that there has to be an electric field in the wire for charges to move. And so how does that happen? Let's say right here I had a battery, right? Let's say I had a battery here, okay? And then the negative end was on this side and the positive end was on this side, right? So this positive end would attract electrons through the wire, and then I'd have a positively charged plate. Similarly over here, the negative end would repel electrons from this side, and then they would collect on this plate. So I've got a parallel plate capacitor. Okay, so that means there's an electric field inside, and there's a potential difference, right? And later on in this chapter, and in chapter 18, we'll talk about properties of capacitors and how we use them to, to store energy, right, for work. So now let's take the battery away. Okay, we take the battery away, and we've got a net negative charge over here and a net positive charge over here. Okay, but the charges are going to distribute uniformly throughout the wire and the plate, and there's going to be no electric field, right? There's no polarity, right? There's no positive and negative charge on either side, so the electric field is zero. Right, we've got a bunch of negative charge over here and a bunch of positive charge over here. All right, so there's no electric field because there's no high charge and no low charge, and there's no connection. Right, there's an electric charge, there's an electric field here between the plate but inside the wire there is none. So once we connect those wires, it doesn't take very long, but once we connect those wires, the system is going to want to approach equilibrium, right? So all these negative charges are going to be attracted over here, right? And so what's happening is there is going to be an electron current going counterclockwise. And so what happens is the polarity of these plates are actually being experienced inside the wire, right? So now there is an electric field inside the wire because the wire says, hey, there's a bunch of positive charge here on this side, and there's a bunch of negative charge on this side. So now there's an electric field inside the wire that's creating that Coulomb's law force on those negative charges, right? So the charges are going to start moving in this direction, right? And so the electric field is clockwise and the charges are moving counterclockwise. So we need an electric field inside the wire. So that means we need a potential difference applied across a wire in order to generate the electric field and generate a current. And so what's going on here is the electron current and the conventional current are actually pointing in opposite directions. All right, now this can be confusing, but the actual movement of electrons in this section of wire is in the positive x direction. The electric field is in the negative x direction. When we first discovered current, we didn't actually know that protons and electrons existed, so we didn't know what was moving. We just assumed that the positive charges were moving. And the terms positive and negative are just our convention, right? They were just arbitrarily assigned to protons and electrons, right? We could have easily switched them, 250, 300 years ago. It would have been just fine. So our conventional current is actually pointing opposite the direction of the direction that the free charges, that the electrons are moving. Okay. Later on, we're not going to concern ourselves too much with this, but it's good to know what direction the electrons are flowing and then how that's related to the conventional current. So they're in the opposite directions. Okay. So current density. Current density is current per unit area. Okay, so it's in amps per meter squared. So my conventional current is the fundamental unit of charge times the electron current. That's this expression right here. It's got all my nice variables in it. So if I substitute this in for my definition of current density, the area terms cancel, and I've got a new expression for the current density, right? So if I knew the drift velocity and I knew the charge density, I could use this expression to calculate the current density. So the current is directly proportional to the electric field. If the electric field is strong, we expect the charges to be moving fairly quickly, right? So if current is directly proportional to electric field, then current density is also directly proportional to the electric field. So your current depends on the electric field, but it also depends on the material. And there's a property of the material that we call conductivity, right? So how well do charges move through a material? Okay, so that's an inherent property of the material, the conductivity. We're going to use a lowercase sigma for that. Okay, so this is a relationship between current density and the electric field. Okay, so this is like a constant. It's kind of like a linear equation, right? Y equals mx. Okay, so current density is dependent upon the electric field strength. We have another property. Okay, if conductivity is how well electrons pass through a material, then the reciprocal of that, or the inverse of that, is what we call the resistivity. Here's that second row that I was talking about. So if you just see a plain old row with units of ohm meters, we haven't talked about ohms yet, but this is a capital omega. Okay, so if you see a row with units of ohm meters, we're talking about resistivity. All right. So resistivity is the inverse of the conductivity. So it's how difficult it is for electrons to be passed through as a reaction to electric field strength. And so I took this table. I think I took it from a different textbook, Randy Knight maybe. But so this table, you see that our metals, right, have very, very low resistivities, right? So if I took the inverse of these values, their conductivity would be very high, right? 1 over this would be a very large number. So we've got silver, copper, aluminum, right? Our metals are very, very low resistivities, right? That's why we like to use them. But then once you start getting into your semiconductors and your insulators, right, your non-metals, you see their resistivities are very, very high, right? It's very difficult to push electrons through with an electric field. So let's go back to our electric field. There's an electric field inside the wire. That means there has to be a potential difference across the wire, right? If we go back to this situation right here, there's a potential difference due to the plates or due to a battery, something like that. So there has to be an electric field inside the wire. Now I'm just concerned with the magnitude here. Okay, I know there's a negative sign here because the electric field is a vector, right? And it points in the direction of decreasing potential. But I'm just concerned with the magnitude here. So we're going to say delta S or delta X or maybe lowercase d, or L is the length of the wire, right? And so I'm going to rewrite my expression for the electric field in terms of the potential difference and the length of the wire. So I've also taken my current density, which is current per unit area, and I rewrote it in terms of current. Okay, I rewrote it in terms of current. Current density is sigma times E, right? It's sigma times E, but the resistivity is the inverse of the conductivity. Okay, so I can substitute sigma E in, but I can also in for J, my current density, but I can also substitute E over rho. So the electric field divided by the resistivity, I'm substituting in here for the current density. Okay, and so that's what I'm doing right here. So my current is proportional to the cross-sectional area, proportional to the electric field strength, and inversely proportional to the resistivity. So that kind of makes sense, right? If you think of a pipe of water, right? What's pushing the water through? E. How large is the pipe? A. And how difficult is it to push water through? Rho. Okay, so that's a nice proportionality, nice relationship right there. But the electric field is the potential difference divided by the length of the wire. So I'm substituting delta V over L in for E. Okay, so I've got this, it's kind of messy, right? It's kind of messy so far, but I've got an expression for the current. Okay, so now we see that the current is proportional to the area, proportional to the voltage applied, right? If you saw in lab that, maybe we'll change the voltage, right? Maybe you're doing pre-lab 4, experiment 4. You see we increase the voltage, the current is increasing, right? Potential difference increases, electric field strength increases, current increases. The longer the wire and the greater the resistivity, the lower the current's going to be. So I'm going to take this expression right here, okay? Because I see a relationship between potential difference and current. So these terms right here, A over rho L, okay, those are all properties of the wire. The resistivity is the property of the material, and the length and the area are all dimensions of the wire. So I'm going to call that resistance. Okay, I'm going to call that the resistance of the wire. So the resistance is the resistivity times the length divided by the area. Okay, and if some of you took physics in high school or somewhere else, you may know what I'm getting at here. Okay, so the resistance depends on the resistivity of the material, but it also depends on the dimensions of the wire. So we're going to call these units the ohm. Okay, so that's a capital omega. So that's the ohm, units of resistance. So if you go back to that table, resistivity is ohm meters, length is in meters, area is divided by, or area is meters squared, so all of my meters go away and I'm left with ohms. Okay. So if I substitute this R in for rho L over A here, so rho L over A, it's flipped right here, okay? So I'm going to substitute R in the denominator. Right? This is A over rho L. So the current is directly proportional to the potential difference across the wire, and it's inversely proportional to the resistance of the wire. All right. So spoiler alert for those of you who are doing experiment 4. This is our mathematical model. I gave you current resistance data, and then I gave you current voltage data. Okay, so this is our relationship. So an amp is a volt per ohm. Oops. An ohm is a volt per amp, and this is my Ohm's law. I equals delta V over R. Okay, so we see that Ohm's law applies to wires, right? Not just resistors or anything like that. So a wire has an internal resistance, and so Ohm's law applies to wires. So I like to write it like this way. Any of you former or current Latin scholars, you might remember that VIR is the Latin word for man. That's what I always use to memorize Ohm's law. Didn't really see the relationship, but it just helped me memorize it. V equals I times R. So I can write it in terms of current, and I can write it in terms of resistance, which I will use very often in my chapter 18 notes. So let's do an example. I've got an aluminum wire. I'm given the charge density, fortunately, so I don't have to go through that whole process again. 2.3 times 10 to the 27 electrons per cubic meter, and it carries a current of 5 amps. So if the drift speed in the electrons is 5 times 10 to the negative 5 meters per second, what's the diameter of the wire? So you could solve for the area and then find the diameter that way. I'm going to substitute an expression in for the diameter, or in for the area that's in terms of the diameter. That's what I'm going to do. So if the wire is 15 meters long, what's the potential difference across the wire? So I've got charge density, I've got current, I've got drift speed, I've got the length of the wire. So I'm looking for the diameter of the wire and the potential difference. And I think I probably, I think I started the second video with this problem. I'll go through it anyway just in case, because I don't exactly remember, but if I go through this example twice, just skip it in the second video. So I'm going to assume that the wire is cylindrical. So I'm going to write the area as pi r squared, but the radius is half the diameter. So I'm going to use this expression for the area, pi d squared over 4. So I'm going to use this equation for my conventional current. Why am I doing that? Because I've got E, I'm given the charge density, I'm given the drift velocity, and I'm given the current. Okay, so if I substitute this expression in for the cross-sectional area of the wire, I now have an equation in terms of the diameter. Right? So I substitute pi d squared over 4 in for the area. I know everything else, and now I can solve for the diameter. So I've got some constants, I've got pi and 4, I've got some values that I know, drift velocity, charge density, lowercase e. So basically I grouped d squared by itself, and I'm going to multiply both sides by the inverse of this, right? So multiply both sides by 4, divide both sides by everything up here in the numerator, and I get an expression for d squared. But I'm looking for the diameter, so I'm going to take the square root of both sides. Now I'm ready to plug in my values. 5 amps, fundamental unit of charge, the charge density was given, which is nice, and the drift speed. So I calculate the diameter of the wire, 1.86 times 10 to the negative 2 meters. Very small diameter, but that's okay. We're usually dealing with very small wires anyway. So what I did was I calculated the area because I'm going to need it for part B. So I plug my value in for the diameter of the wire, and I calculated the cross-sectional area of the wire. So I get 2.72 times 10 to the negative 4 square meters. So the second part says the length of the wire is 15 meters long, and we need to know the potential difference. We need to know the potential difference across the wire, or the voltage. So I know the current from part 1. I just calculated the cross-sectional area. I consulted my good friend the internet and looked up the resistivity for aluminum. Actually, I got it up here on the chart too. So there you go, 2.82 times 10 to the negative 18 ohm meters. So I know my resistivity, my length, my cross-sectional area, and my current. Okay, so I'm substituting rho L divided by A in for the resistance. So once I calculate everything, 5 amps, resistivity, the length, the area, I get a very small voltage, right? 7.8 times 10 to the negative 3 volts. Moral of the story is, with a conductor, it doesn't take a whole lot of voltage to be applied to generate a high current, right? See, we have a very small potential difference, but we're generating this is a fairly high current, 5 amps for this type of wire. Okay, so I'm pretty sure, I'll double and triple check, but I'm 99% sure that I did this example in the second video, so I'm gonna stop while I'm still under my time limit, and hopefully I kept it short enough that this will the video will encode properly and we won't have any more audio issues. So sorry for the delay. If you run into anything, you have any questions, again, feel free to get in touch with me anytime. Alright, thanks.